All right, so let's talk about systems of linear equations. The idea of a system is that there's more than one equations. And you probably heard in high school something like, if there's two equations, you can have two unknowns. If there's three unknowns, you need three equations. However many unknowns you've got, you need that number of equations. Unknowns are things like x and y, maybe. So, let's just talk about x and y's. In the last section, chapter 1, we were talking about linear equations, and we were graphing them. So there's three types of ways that two linear equations can interact with each other. Let's draw ourselves some x and y axes. They could be parallel to each other. I could have two lines in my system, and they could be parallel lines. I could have my lines looking like this, where the one line is there, and then right on top of it, I'm drawing the second one thicker and clear, but you get the idea. Right on top of it, there's the other line, so they're right on top of each other. And lastly, I could have maybe what we normally imagine, where I've got two lines. Let's try to make these not look perpendicular. They could be, but they don't have to. That looks like a bad two. I don't know. Here we go. Where they have this one single point where they're crossing. These lines work like this. This one right here would be called no solutions. The lines are parallel. They never meet. There's no common ground between this line and this line. They never cross. This one right here would be infinite solutions. The two lines are exactly the same. They may have looked like slightly different equations, but deep down inside they're the same, which means they share all the same points. It's one line right on top of the other line. There's no difference. And finally, this right here would be a one-solution system, because there's this one single point where they meet. Let's look at what the equations would look like. If you recall from the last section, parallel lines have the same slope. So if I've got my line in standard form, x plus y equals 3, another thing that might do this would be the equation 2x plus 2y equals 8. The way I could see that these were the same lines is I would solve this top one for y equals negative x plus 3, get it into y equals mx plus b form so I can identify the slope. And then I do the same thing down here. 2y equals negative 2x plus 8, divide everything by 2, and I'd find out that y is equal to negative x plus 4. These two share the same slope, and that means they're parallel lines. Because these two numbers are different, I know they're not one line on top of the other. So, because if you've got the slope sharing is the same, but the y-intercept's different, then you know you have a no-solution system. On the other hand, if you've got x plus y equals 3, and then you have 2x plus 2y equals 6, if I solve the top one into y equals mx plus b form, I'm going to get y equals minus x plus 3. But if I solve the bottom one into that format, once I divide through by 2, I get y equals minus x plus 3. The slopes are the same again, but much more importantly this time around, the y-intercepts are the same. That means it's the same line. They looked like two different equations, but they weren't really. That's the case of infinite solutions. No solutions means there's no answer to the question that I've posed. Infinite solutions means there's infinitely many answers, and that basically means the question wasn't actually interesting. I was secretly asking about the same two things. But it's one solution that we're the most interested in. This is the most exciting, because we get to find out, where is this common ground here? How do I find this answer? And these sorts of equations are going to have different slopes, and they're going to have perhaps different y-intercepts as well. And these are the ones we want to talk the most about. So, having mentioned that, you've got some things in the homework for this section that asks you, it gives you some line equations, and it asks you, solve them into y equals mx plus b form, decide if their slope's the same. But it also has some things where once you are given it, you actually can solve and find the answer. I'm going to refresh something that you might have last seen with us in college algebra. called the addition method of equation solving. As soon as we get into the next section, we'll talk about a more advanced finite optimization math method, but for right now, let's talk about this. But I'm going to talk about that solution process, which I think is called the addition method in this textbook too. Certainly it is in college algebra. And I'm going to talk about it in terms of a word problem. So here's my word problem. The Old Coffee Shop sells a special blended coffee that costs $5.60 per pound. It is created from two separate organic sources. Each is exactly 5,324 miles apart from each other on the opposite sides of the world. The first is picked by an ancient order of monks and costs $5 per pound, while the second costs $6 per pound and is picked by an all-volunteer workforce of Gibbons who are paid a living wage. If the independent owner mixes a blend batch of 100 pounds, how many pounds each of Monk coffee and Gibbons coffee are needed? So this word problem illustrates very well what was mentioned in one of the sections of Chapter 1. You have to go through a process. First of all, notice that I started highlighting some things that I thought were key numbers. Notice some things I didn't highlight. This right here has nothing to do with what we're asking. It doesn't matter. The fact that they're separate sources doesn't matter. They're organic doesn't matter. It doesn't even matter particularly that monks or Gibbons pick it. I mean, they're all volunteer, but really, who cares? They're paid a living wage, that's great, but we're not here to discuss the politics of the situation, and I don't even care about opposite side of the world. There's some things on the word problem that are completely pointless, but this is great that we have them in here because in real life there's stuff that's completely pointless. Now, I've done my best to make these pointless things look patently ridiculous, but in real life you've got a lot of things that are useless to solving the problem. What we need from here is two things. I'm asking how many pounds of each. How many pounds of Monk, how many pounds of Gibbons are needed? I look through here carefully, and I don't see the answer buried in the story problem in an obvious sort of way, which means I've got two variables. In the last chapter, I talked about how it's important to use the right letters. You don't want to use uppercase when you should use lowercase because that'll make it harder for you to communicate between the book and what you're doing. In the same way, it's not always correct to use x and y as your variable. Here, I've got a very clear variable for this and a very clear variable for this one, m and g. That's going to mean that when I get my final answer, it's going to be easiest for me. Now again, you can translate it to x and y if you like. The way you would want to do that if you were is you would clearly label this as the x, and you would label this one here as y. You would just give me a heads up in your solution process so that you'd know what's going on. And in WebAssign, you're probably going to use x and y a lot. But when you're actually trying to work through and think something out, it can help to use some good variables. So here's what we've got. We've got these two things. First thing, I have to decide what exactly m and y mean. And I know what m and y mean when I look here. I'm trying to find pounds. So m should be in pounds and y should be in pounds. And that gives me my first equation. M plus y equals 100. However many pounds of this plus however many pounds of this should equal the 100 pounds that the store owner mixes up. Next, I need my second equation. My second equation, I somehow have to build up. I've already used pounds. I've already used these. I need to keep the same letters, so it still should involve m and y, and it should still equal something. Now I'm going to use the only other piece of information the problem gives me. It gives me information on cost. So this first equation is a pound equation. My second equation here is going to be cost. And what do I know? The Monk coffee costs $5 a pound. So 5 times pounds, this will give me total cost of Monk coffee. And if I add to this the $6 a pound of the Gibbon coffee, I'm doing y here, aren't I? I give that wonderful little talk about G and go right back to y. $6 per pound will give me the total cost. of the Gibbons coffee. Which means finally, if I take the fact that when I mix them together, they cost $5.60 a pound, if I do 5.6 times 100, because I make 100 pounds of the blend, and the blend costs $5.60 per pound, this will be my actual total cost. Total cost of blend. So these are my two equations. If I multiply them out, I have 5m plus 6g equals 560 once I do 5.6 times 100. And then I have m plus g, equals 100. And now I'm going to solve this using the addition method. The addition method is you put the equations together, you make sure that all the columns match up correctly, so you've got the m columns in line, the g columns in line, and the constant columns in line. And then what you do is you go through and you multiply the bottom equation by a clever number, and this clever number should be a good number that will make it so that when I add the two together, one of the columns in the top line goes away. So my clever number is -5. I'll multiply the bottom equation through by -5. And when I do that, I get this. 560 minus 500 leaves me with 60. 5m minus 5m leaves me with 0. And 6 minus 5 leaves me with just g. So g equals 60. Then I take this information, I plug it back in my original equation, and I get m plus 60 equals 100. So I know that m has to equal 100 minus 60, which equals 40. The last step to any word problem is going through and making sure that you've answered the correct question. How many pounds of each of Monk's and Gibbon coffee? Monk coffee was 40 pounds. Gibbon coffee was going to be 60 pounds. That's how much I'm going to be buying of each of these. Notice something. In the word problem process that we discuss, you read the real world information, you start to create your model, you solve your model using the techniques of the section we're in, and then you get your answer, but we should always take our answer and go back and compare it to the real world. If the Monk coffee costs $5 and the Gibbons coffee costs $6, does it make sense when my average coffee price is $5.60 that I've got more of the more expensive coffee? And the answer is, of course, yes. If I'd done more of the Monk coffee, my average price would be closer to $5. Since my average price is $5.60, it's closer to the $60, which means I was expecting to use more of the Gibbons coffee. So my actual answer makes sense in a sort of street smarts or real world way. And you always want to do that real world check. This will prevent you from making the sort of, crazy mistakes. Later on, we're going to talk about some financial stuff. And it's going to be very easy in that section to cook up a number and say, oh, my monthly payment's going to be $2,000. And you're going to do that for, 30 years. And suddenly you realize that makes no sense because you're only trying to save up $4,000. And $2,000 a month over 30 years is going to be, hundreds of thousands, if not a million. So you do that real world common sense check. This is the addition method. Again, you've probably seen it in a linear algebra 2, maybe in high school or college algebra class here with us at the college. We're going to go on in the next section to talk about a more advanced way of solving this stuff, because I could have just as easily, instead of having m and g, I could have had n, g, and k. I could have added more variables.